Thank you for investing your time to learn about GeoSierra and our specialized trenchless technology for installing permeable reactive barriers, better known as PRBs. GeoSierra is a highly specialized firm focusing on the design and installation of PRBs. We complete each project on a firm fixed-price basis and warrant that each PRB will be installed according to all specifications for height, depth, length, and thickness. And critically important, that the PRB will be permeable. In this video, you will learn about the exclusive start-to-finish QA/QC tools and processes that enable us to offer and validate our warranty. The reality is, without these QA/QC processes, the client has no way of knowing if the newly installed PRB is actually going to work as planned. By eliminating the need for a trench, GeoSierra has broken through the shallow depth limits of trenched PRB construction methods. We've been perfecting our trenchless technology since its discovery in 1992, and it is well established with 15 full-scale PRBs installed, 5 of which extend deeper than 100 feet. Because it only requires a 6-inch borehole approximately every 15 feet, our trenchless method is agile for working around underground utilities, close to active manufacturing sites and high urban traffic areas, and even within an active railroad right-of-way, where trenching is not permitted because of the potential damage to the railroad track. And because trenching is not necessary, the process is clean and urban-friendly, generating only minimal soil disruption and waste disposal issues to deal with. GeoSierra has been continuously improving the trenchless technology since 1992, when Dr. Grant Hocking discovered that it would be possible to create and control a single vertical fracture in stratified geologies from soft sands to heavily consolidated sediments like this cemented peat. Over 200 field experiments were conducted from 1992 through 1997, with the first full-scale PRB installed by the trenchless method in 1998. By the late 90s, proprietary design, equipment, tools, and QA/QC had been perfected to a point where 4 patents were awarded from 1999 through 2002. The trenchless PRB consists of a wall of permeable iron filings which are transported to the subsurface by a high-purity gel consisting of water and a food-grade starch, hydroxypropyl guar, or HPG. The gel in this form is water-soluble and kept in these 3,000-gallon storage tanks and then pumped to the frac mix hopper.
The gel, here it is mixed up in the uncross-linked state, and at this state it's water-soluble and it has a consistency of like glycol, you can see here. This is food-grade, high-pure food-grade starch. Now what happens then is we add a cross-linker to this, and this cross-linker, I'll bring Jim over here to show you what it really looks like. So this same material, just a very small amount of cross-linker is added, and it becomes so viscous that it basically, we are having trouble holding it. Then we add the iron to it, and it may look a little bit of a dirty color because of the iron, but it's the same material. And it's very difficult to even get it out of this little bucket. It is so viscous, as you can see. It just carries its own weight. This is carrying iron, a specific gravity of 2, and that is all cross-linked and gets pumped down the hole. Now there's an enzyme added to this, and all that gel is basically, all this is water, and it just breaks down to water and sugars and leaves a permeable iron barrier in place. The iron comes in 3,000-pound bags and is lowered onto this hopper. Now this hopper has skirts around it and is connected to our bag housing, which is a dust collection system. So there's a very high vacuum applied around this hopper, and as you see, Chad doesn't need to wear a dust mask because it's engineered. It's all very clean, you don't see any dust emission, and the iron's loaded into that hopper. Then the hopper is taken up on top of the mixing pumping skid, and you'll notice that it also is connected to the bag housing to that high vacuum pump. And these skirts around this stop any iron dust whatsoever. All the air is actually pulled into the system, into the bag housing, and it's totally dust-free.
The iron filings and uncross-linked gel are mixed by the frac mix unit, with the enzyme and cross-linker added on the pressure side of the duplex frac pump. The cross-linked gel, now in its highly viscous form, has the strength to propagate the fracture and carry the iron filings to their destination. Within a few hours, the enzyme breaks the gel into water and sugar, leaving a wall of permeable iron filings.
How we actually do this is we do this by an injection technology which is under very low pressure and basically just displaces the soil and puts this iron PRB in the ground. Each one of these wells, they aren't wells, they are frac casing systems, and Sam Wells is showing one here. It consists of 2 segments, and these segments are aligned along the azimuth in this direction of the PRB, and in this particular PRB there's 4 of these in each one of these casing systems from a depth of 100 feet up to 18 feet. And this is the casing system. This is a cutaway section of that 10-foot casing we saw. Here's the 2 pieces of aluminum which have delimiters, and it's grouted in a 6-inch hole, and then this is all closed up initially. So initially it looks closed up and grouted up. Then we open up and inject the iron and open up the casing like that. And that dilation of this casing and the grout is enough to trick the ground that you've created an artificial fracture in this direction. And it's very important that you don't pump it at high pressure. This is going to be at very low pressure, because if you pump it at high pressure, it will just turn to the minimum stress, to the maximum stress direction. So you've got to stay and just keep it at about, we do it about 5 psi greater than the horizontal stress at depth. To be able to see subsurface as we're doing this, we have these resistivity strings which are shown here. They're downhole and they listen to a 100 hertz signal. We basically, as we're pumping the gel into this casing, we excite it with a 100 hertz signal, low voltage, and these receivers pick it up and they image it, and you can see in that frac track instrumentation trailer the image as it's being injected. And you'll see, and we know then we can actually see and confirm that we've built it as per spec.
And how do you control how wide it is?
Oh, okay, you shoot it first and you've got to coalesce, and the first time up it might be about that wide. And then you wash, we have to actually wash the frac casing out, and that's why it's got delimiters and the ground pushes back on it. So we wash it out, take all the iron out of it, and then re-inject. And what happens is when you re-frac it again, this permeable iron that you've got there already, it's like a big suction cap. It wants to stick to it because it's losing leak off to it because it's more permeable, and it just actually goes right along that whole, straight along the edge of it, and we'll actually build it up. So here we're running it with 3 injections per 20-foot panel section. So to build the thickness of 4.5 inches, we actually do 3 injections. We'll start them off, coalesce them, and then come back in and do other injections.
To inject the gel and iron filings, 6-inch boreholes are drilled approximately every 15 feet on the azimuth or bearing of the PRB. The pre-aligned frac casings are then installed, and a downhole camera and compass are used to verify the casings are properly aligned in the borehole. With proper alignment confirmed, the casings and feeder pipe are then grouted in with cement to be tightly packed in the formation. The PRB is built from the bottom up, with packers placed in the feeder pipe to seal off the injection target area. Here we see a close-up of the packers being inflated. The gel and iron filings are then injected at low pressure, typically 100 to 200 psi, depending on depth, causing the casing to dilate along its entire length, creating a vertical and lateral fracture pathway for the gel and iron filings to follow. The frac wells are injected alternately, with the odd-numbered wells first. This is done in order to harness the power of pore pressure relief, so absolute control of each frac pathway can be assured. The packers from 1 and 3 are then pulled, and the wells are open to the atmosphere, providing the pore pressure relief pathway that ensures a continuous and completely coalesced PRB with no gaps or voids. With the lower section completed, the casings are washed out and the process is repeated to complete the PRB. And again, pore pressure relief assures both vertical and lateral coalescence. With our patented active resistivity imaging technology, we're able to see in real time each PRB segment as it's being formed. The red image simulates the 100 Hz signal being transmitted by the electrically excited gel and iron filings. This signal is picked up by the downhole receivers and is being transmitted to our FracTrack computer system. Because it's conductive, as each new segment coalesces with the neighboring vertical and lateral segment, it in effect closes the circuit, lighting up the entire coalesced portion of the PRB. The Trechless technology is ideal for sensitive urban sites like Kelly Air Force Base, where 2,100 feet of PRBs were installed in 2004 beneath 2-lane streets congested with underground and overhead utilities in the city of San Antonio. Because there were no trenches, the project was safe and minimally disruptive for the residents of the community. The best possible location for the other 1,500-foot-long PRB completed for Kelly Air Force Base in 2005 was within an active railroad right-of-way, only 26 feet from the tracks. Trenching this close to the railroad tracks would be out of the question, but GeoSierra's trenchless technology made the installation feasible and acceptable to the railroad company. As you can see, the footprint required for the frac equipment setup is flexible, allowing operations in tight spaces with an installation reach of up to 200 linear feet of the PRB without having to move. At Tinker Air Force Base in Oklahoma, there were no site access problems or urban density issues, but damage to wildlife habitat had to be minimal during construction, allowing for full restoration of the site to its natural state upon completion of the PRB installation. The Tinker PRB had to extend from a depth of 70 feet to 95 feet below ground surface in an aquifer containing interbedded layers of cemented sandstones. Very tough geology, but not too tough to keep a 500-foot-long PRB containing 330 tons of iron from being installed by the trenchless technology. In the early 80s, DuPont discovered groundwater contamination at this former manufacturing site in Oakley, California, bordering the San Joaquin River in the Bay Area. Following extensive analysis, DuPont installed a pump and treat system in 1989. At the time, permeable reactive barrier technology had not yet been discovered. After 10 years of pumping, DuPont decided to evaluate alternative remedies because the pump and treat was not effectively removing contaminants and was not containing the plume. Furthermore, operating the pump and treat was consuming enough energy to power 220 homes in the Bay Area and was costing DuPont $1 million a year in operations and maintenance expense. After evaluating alternative remedies, DuPont, with regulator approval, decided to install a pilot PRB in early 2001. Represented here by the yellow line, the pilot PRB is 110 feet long and extends from a depth of 45 feet to 115 feet deep. After installation of the pilot, the pump and treat system was shut down so it would not interfere with the monitoring of the pilot PRB. The pilot proved to be so superior to the pump and treat system that it was never turned back on and has not operated since early 2001. After 4 years of monitoring the pilot PRB, a February 2005 Berkeley Department of Toxic Substance Control fact sheet summarized results this way. The pilot PRB was 3 to 4 times more effective than the original pump and treat system. The removal of carbon tetrachloride approaches 100% effectiveness with the pilot PRB. Because of the pilot PRB's outstanding success, DuPont engaged GeoSierra to complete the balance of the PRB to its full-scale dimensions in 2005. Here you see a clay layer separates the upper and lower aquifer, so to avoid vertical migration of the contaminants, 2 PRBs were installed in parallel. The first PRB extends 375 feet in length from the pilot at a depth from 55 feet to 115 feet below ground surface. Up gradient, a second PRB 485 feet in length extends from the depth of 30 feet to 60 feet. The PRBs overlap to intercept a saturated sand lens running through the clay layer, but do not penetrate completely through the layer, thus eliminating any chance of vertical migration of contaminated groundwater. People are consistently amazed by the amount of iron that can be installed by the trenchless installation method. The DuPont pilot contains 330 tons of iron, and the extension an additional 1,440 tons. Each of these bags of iron weighs 3,000 pounds, and there are 1,180 of these bags of iron in the 2 PRBs. As further evidence of the amount of iron installed, here we see the empty pallets used to carry the 960 bags of iron used in the extensions. Following construction completion of the PRB, an inclined profile soil resistivity probe, guided on a 30-degree angle from vertical, is used to determine the precise thickness of the PRB. As shown here, the drill rig must be offset a considerable distance from the PRB in order for the resistivity tip to intercept the PRB at the specified depth. A hollow stem auger is used to drill to approximately 10 feet from the location of the PRB. The auger is then stopped and the resistivity probe is lowered through the auger until it reaches undisturbed soil. From there, the resistivity probe is driven through the soils. When it contacts the iron filings, the resistivity changes dramatically and then changes again as it emerges from the other side of the PRB. The precise thickness of the PRB is then able to be determined. The incline profile method was done at 10 locations specified by DuPont on the PRB, and all were within design specifications. The DuPont Oakley site is a perfect example of how passive in situ permeable reactive barriers are the ideal remedy for remediating deep groundwater and also protecting the wetlands. In a recent local newspaper article, Oakley city development officials referred to the DuPont site as the crown jewel of Oakley. By enabling the removal of the pump and treat infrastructure, the PRB has eliminated what would otherwise be a major flaw on the surface of this crown jewel and is helping bring new life to the site as it begins its transformation to a new day.